All right, folks, let's get after it here on page 5. We're talking about leaking helium. Thrilling topic. After buying many helium balloons only to see them deflate within a couple of days, Aaron and Jenna decided to test if helium-filled balloons deflate faster than air-filled balloons. By the way, I don't know if you guys know Aaron and Jenna, but they have a lot of time on their hands. Anyway, to find out, they bought 60 balloons and randomly divided them into 2 piles of 30. That's one of our magic numbers in statistics, so I think you can see where that's going. They filled the balloons in the first pile with helium and the balloons in the second pile with air. Then they measured the circumference of each balloon immediately after being filled and again 3 days later. The average decrease in circumference of the helium-filled balloons was 26.5 centimeters, and with a standard deviation of 1.92. Average decrease of the air-filled balloons was 2.1 centimeters, with a standard deviation of 2.79. So I would like to quickly here summarize the sample statistics that we have in this problem. Let's first talk about helium-filled balloons. So we have an X bar here. I'll use the subscript H of 26.5. Standard deviation of 1.92. And the sample size there was 30. Let's go ahead and look at the air-filled balloons as well. I'll use a subscript of A. The mean of the air-filled balloons mean decrease was 2.1 centimeters. And the standard deviation was 2.79 centimeters. And we also had, oh, look at this, folks. Here's a mistake. Did you catch that? It's not S sub X. It's S sub A for air. Last but not least, we had a sample size for air of 30. Let's go ahead and take a look at what the problem actually asks us to do. Do these data provide convincing evidence that helium-filled balloons deflate faster than air-filled balloons? As is always the case with this type of problem, we are going to do the 4-step process, and we'll start with state. We need to test a null hypothesis of, well, a null hypothesis here, we want to see, obviously, if you go back and look at these means, obviously, the helium-filled balloons lost more circumference than the air-filled balloons, but is it enough to provide convincing evidence to say helium-filled balloons deflate faster? So our null hypothesis is going to be that they don't deflate faster, that mu h minus mu a is equal to 0. And that'll give us an alternative hypothesis of mu h minus mu a is greater than 0. This is a one-sided test. We're going to do this at a significance level of alpha equals 0.05. And I'm going to define my parameters. Folks, that was a long one. Notice that I have thoroughly defined my parameters mu h and mu alpha, mu sub a. Some of you like to shortcut the step here. Please don't do that. I don't want you to lose points on the AP exam because you didn't thoroughly define your parameters. All right, next up in our 4-step process is the plan step. We are going to perform a 2-sample t-test if conditions are met. Let's go ahead and check those conditions. Notice here, folks, I use the word treatments because this isn't an experiment. We're applying a different treatment to each grouping of balloons, and that actually affects what we're going to say about the 10% condition. 10% condition is not necessary here because there was no sampling. Yes, we bought some balloons and we pulled balloons out of a bag, and you might say, well, isn't that a random sample? Yes, but we assigned treatments randomly, and that is not sampling. Okay, now let's go on to the last condition we need to check, which is the large sample condition. And we have both n sub h greater than or equal to 30 and n sub a greater than or equal to 30, so that condition is met. It's now time to take a look at the do step. We've met the 3 conditions required. We can now perform the inference procedure. As I mentioned before, we're going to do a 2-sample t-test on our calculators. And I'm going to show you those results from the calculator right now. Remember, this is a menu. 6, 7, 4. And when you run this test on your calculator, you're going to get the following. You're going to get a test statistic of 39.46, and that is massive. You're going to get a degrees of freedom of 51.44, and again, that's not something we're going to calculate manually with that crazy formula. And then be careful with the p-value here. I'm going to show you what the calculator gives you, and then I'm going to help you read it. It's this 1.983. Gives you something like that. That's exponential notation, folks. Don't be confused by that. That's 1.983 times 10 to the minus 40th power, and that's approximately 0. Okay, I do have a special little treat for you now. I am going to play you a quick video within this video of the calculator operation. So let's zoom out here real quick and then zoom in here. Folks, this is the TI Nspire app for the iPad, so this will look a little bit different than yours. Don't be alarmed. It will work the same way. So I'm going to go ahead and open a calculator page. And again, I know this screen looks different than your handheld, but the menu options are the same. I'm going to go ahead and select Statistics, Stat Tests, and then the 2-sample t-test. Data input method here, it's not the data. We need to select the stats option because we have the summary data from the samples. And then I'm going to go ahead and enter my values for the mean of the helium data, standard deviation of the helium data, sample size for the helium data. And then we'll move down to the air treatment. Mean was 2.1, standard deviation 2.79, sample size was 30. Now be careful here with the alternate hypothesis. We had mu1 minus mu2 is greater than 0. When you look at the options here, you'll see that that isn't one of the options. So you have to select the appropriate one, which is mu1 greater than mu2. That's what we're testing. Do the helium balloons lose circumference faster? Last but not least here, this final thing is called pooled, and I will suggest to you that you always, always, always select no on that option. It's always no pooled. And if you want to know more about why, please take a look at your textbook at the end of section 10.2. There's a little blurb about why we always select no for the pooled option. All right, folks, that's it for that little fun video. Let's go ahead and take a look at the results. We have the results from our 2-sample t-test. You can see we've got the t-value here of 39.46. We got the p-value of 1.983 times 10 to the minus 40th, and that's a super small number. Also, that's where you're going to get your degrees of freedom, unless you want to use that very large and cumbersome formula. All right, let's go back to the notes and see where we need to go from here. It's time to make our conclusion. And our conclusion is based on the p-value. The p-value of about 0 is way less than our significance level. So we reject the null. We do have convincing evidence that helium-filled balloons deflate faster than air-filled balloons. Now you know, folks. Okay, so that's it for the 4-step procedure on that problem. That's a significance test. Comparing two means. Let's see what we're left to do down here in part B. Oh boy, the dreaded interpret the p-value question. So let's talk about what that p-value means in the context of this study. Assuming the null hypothesis is true. And remember that null hypothesis was that mu h equals mu a. So assuming that is true, the probability of getting a random sample mean difference of 24.4 centimeters or more. Where 24.4 come from? That's 26.5 minus 2.1. X bar H minus X bar A. The probability of that occurring is about 0. Boom. There you have it, folks. We have one more to go. Hang in there. You can do it.